this symbol, EG, degree, and this vertex, the V. So for example, we can say the degree is degree B is 3, and for the C, 1, 2, 3, 4, we have 4 edges. So degree C, degree 4. So the degree, we can just the metric about the edges, so how many the counting. It means if just more edges connect with the node, we can say this node maybe it is busy or it is very important. For example, in the computer network, if some the node have many than edge you connect with them, that means it is a higher degree we can say this node is very important because many nodes connect with it. So it is a degree concept. And this theory just gives about the degree and the edge is the relationship. That means if for the undirected group, if there is an undirected graph, that means we have no direction for each the edge, no arrow connect with the edge. And then we have these rules. That means all the edges degree, their summation equal to 2 times edges. This is E. This E means is edge set. So here, 2 bar for E, it means all the edges, the number of the edges. And for this, maybe we have just some concrete example from the video. Just give you to share more about this meaning. Okay.
So we're going to start by looking at some terminology that you need to understand, and this is specific to undirected graphs. We'll look at directed graphs in a few moments. And the first is adjacent vertices, also called neighbors. And this one's kind of a gimme. Adjacent vertices are vertices that are connected by an edge. So A and B would be adjacent or would be neighbors, but B and C would not because B and C are not directly connected by an edge. Incident would be what we would call an edge. So we would say, let me just give this edge a name B. So I would say edge B is incident with vertices E and B. So incident just means it's the edge that is connecting two vertices.
So here maybe we didn't mention now, maybe later we are mentioning this incident, and incident can be seen as connected with the two edges, and it is similar. But these adjacent vertices can be seen the neighbors. Neighbors, how to say B, what is the neighbors E? That means it is just to have edge connected together. So if they connected together, we can say it is a directed neighbor. For B, A and E is a neighbor of the B because they have edge from A to B and from E to B. So we can say like this. Okay.
If we talk about the neighborhood, and you see on my next line, this is actually the notation that I would use for a neighborhood. A neighborhood is essentially just a set of all of the vertices, which of course would be a subset of the vertices of the graph, that are connected to a specific vertice. So if I wanted to know the neighborhood of, say, E, it would be the union of all of the vertices that belong to the set that are neighbors. So that would be A and B and C. So obviously D would not be included because D is not connected to E. That brings us to degree. The degree for an undirected graph is essentially the sum of the number of ins and outs. So the number of vertices connected to that particular vertice, so the number of edges connected to the vertice. So for A, notice we'd have 1, 2, 3, 4.
Here should be careful for the, the loop. This edge is a loop or circle loop or circle edge. Then should be careful. They are just for the degree. They have contributed 2 degrees because they come from the yin, come from the A, but also end to the A. So we have the 2 edges connected with the note. So for the loop, we should to connect the two edges for the A. So the degree A we have 1, 2, 3, 4, not 3. We have only say it is just the one edge, but it is a special edge. It is a loop edge. It is a beginning point and end point are same A. So here for the loop, we just for contribute this S degree is 2.
So the degree of A would be 4. So even though that loop is just really a line connecting itself, we do have to count it twice. For B, we have 1, 2, so the degree of B equals 2. If we're looking at E, the degree of E is 3. And then for C, 1, 2, 3, degree of C is 3. And then for poor D down here, the degree, of D is obviously 0. So it is a vertex, but it is not connected, and therefore it has a degree of 0 because there are 0 edges coming out of it.
And the rest of the 2 concepts, maybe we didn't mention our slide, but you can maybe you can use it to understand. It can be seen as it's a handy concept. You can to understand from this video.
We would call D isolated because obviously it's not connected to anything else. The last one is a pendant, and unfortunately I didn't put that on your picture, but a pendant would be something that is essentially just connected to one other edge. Let's say I had a square, and then I had a guy sticking out like this. And so the pendant would be this guy because he is out here by himself, and it is the vertex that is the pendant. So if this was point E, just call these A, B, C, D. So E would be the pendant because it is the vertex that is connected only once to another vertex.
So here just to show you from this video, many of about the concrete example of the concept. And here just to give you some this relationship between just the rules for the all the degree and the edges. Some of the edges this is just it is a relation. That means, for example, how many edges are there in the graph of the 10 vertices, each of the degree 6. So it is just to say that we have the 10 nodes. We have the 10 nodes, and for each the nodes, its degree is the same, is the 6. So how many? It is mean that we have the 10 times 6. We have the 60 degree. It is all the degree. And from these rules, maybe we can say it is the double the edges. Double edges, that means 2 times the edge or the edges. So edge is equal to 30. We are just using this theory to give this result. So how to understand why we have these rules? That means all the degree is equal to 2 times h. Maybe from the degrees of definition, maybe we can understand, because we know that for each of the vertex, if you have an edge, that means it is this edge, because we know that each edge connects the 2 nodes. or two points. So that means each of the edge will contribute the 2 nodes each the 1 degree. That means if you have one edge, then the 2 nodes, for example, this edge is connect A to B. So this edge will contribute A 1 degree and contribute B also another 1 degree. So each of the edge will contribute 2 degree. So 2 edges will contribute 4 degree. And the 3 edges, all the 3 edges will contribute the 6 degree. That means, for example, you you just here is 1, 2. We just give 2, the 2 edge because each of the edge will contribute 2 degree. For example, this is the edge 1. Edge 1 here is edge 2. The edge 1 will contribute. Here is A, here is B, here is C. The vertex edge 1 will contribute A 1 degree and contribute B another degree. So similarly, for edge 2, contribute A degree, contribute C degree. So we will find each edge will contribute the 2 degree. So each edge contribute 2 degrees. So all the edges just the time 2. We are just get all the degree. Here means all the degree. This V is all the vertex, all the nodes, and E is all the edge. So all the edges, each edge contribute 2 degrees. All the edges should be double the edges. So 2 times edge is equal to summation of all the degree for all the nodes. So just based on these rules, we can to solve many other questions. For example, if a graph have 5 vertices, can each of the vertex have degree 3 or 4? So how to check whether or not this to satisfy this condition? Because we have the 5 vertices. We have 5 nodes. So 5 nodes, that means we just all, it is 5. So we can say the 5 times, equal to, this is a vertex. So each of the, here say each of the vertex have the degree 3. So altogether node, it is 15. So if the 15 means that it is maybe the double or 2 times edge. So because we know that edge should be integer, you cannot say it's 1.5 edge. You have just the whole edge, it is integer. So, but now we will find it is just the odd number. It is 15. So cannot just because this if just from the rules they will find is 7.5. 7.5 it is not right, or it's not integer. Okay. So if we just have the 5 vertices and for each the vertex have the 3 degree 3, then we have altogether degree is 15. 15 cannot be some the double edge. So it is odd number, not even number, not possible. But for the 4, maybe possible. For 4, we have 20. So 20, it is an even number, so we can say edge maybe 10. Possible. So from these rules, we can to simply determine whether or not some the degree or vertices, whether or not they satisfy some these condition or these just the rules. Okay. And here just have a video more about some about this degree. this is just also can be seen the example if you just using all these rules.
Let's take a look now at
just mean how many edges. Just talk about the vertex and have the degree. It is a concrete example, but just based on the rules may be easy to understand.
the handshaking theorem, and you might not see this called the handshaking theorem everywhere, but it is a theorem or a relation that we're going to use often in graph theory. So
for this question, it is maybe is concrete the real question and the human word. But if just to translate the graph and graph concept, then it is the handshaking can be seen as H. If handshaking B, then we can connect A and B using H. And BC or BD have a handshake, and that means we're just using the H. So we can to change or translate our real question into a graph theorem. Okay? And in fact, this graph theorem can also be as a set theorem. And also, set theorem also based on our just the predicate or logic. So then we can use the computer to solve our real question, just like this.
So the handshaking theorem essentially initiated with a question like what I have written in green. Suppose there are 6 people in a room and each must shake hands with every other person. How many handshakes occurred? So without looking at the handshake theorem, let's just look at what the solution is. If I started, and again, if I have an edge connecting 2 vertices, that means they shook hands. So A shook hands with B, that's 1. A shook hands with C, that's 2. And then with D, that's 3, 4, 5. So then if I look at B, remember B, I don't have to count the one I've already traced over in blue because I've already counted that A shook hands with B. So B shakes hands with C, D, E, F. So that's 4. And then I'm going to add and one more 3 over here, not an initial 3, but 3 more for C. And again, that doesn't mean C only shakes hands 3 times. It means I've already counted that he or she shook hands with A and with B. And with D, I only have 2 more that I haven't counted. And with E, I only have 1 that I haven't counted. And if I add up 5 plus 4 plus 3 plus 2 plus 1, I get a sum of 15.
So from this, it is just first translate this edge and then just using our the counting rule, or just I will have mentioned in the previous chapter, it is counting, just using the counting to solve out this question.
So what I know is that there are 15 total handshakes. So if they just asked for how many handshakes, I've answered the question, I can be done. But we want to think about this more mathematically than having to count this up every time. So instead, let's think of it this way. And we did a question like this before, so you may be thinking, oh, Professor Brame, you're cheating. You're using an example we've used before, and I totally am. I'm totally doing that. Here's what we said before. We know that A obviously is not going to shake hands with him or herself. That would just be weird. But A has to shake hands with B, C, D, E, and F. So that's 5. And B shakes hands with 5 people, and C shakes hands with 5 people, and D, and E, and F. Now, if I add all of those up, I in fact get 30. Well, we know our solution is 15. We've already discovered that on our own. And 30 is not the correct answer. But what we talked about before is that if A shakes hands with B, then B is shaking hands with A at the same time. So essentially what I've done is counted it twice. So what the handshaking theorem says is that for some graph, and remember the terminology there is BE, where B represents the vertices and E represents the edges. And let's just say that this has M edges. Then the handshaking theorem says if we take 2 times the number of edges, that is going to equal the sum of the degrees of all of the vertices. So does that say exactly what I said before? Well, let's look at it this way. We already know that the sum of the degrees of all of the vertices for this picture over here is 5 times 6 because there are 6 vertices and the degree of each is 5. 1, 2, 3, 4, 5 edges coming out of it. So that's 30. This is saying that is equal to 2m, where m is the number of edges, and 2m obviously would give me that m is 15, and that was my solution. So essentially, it's just an easier way to go about finding the solution.
So these just give us the two ways to solve this question. The first, we are just using the previous counting rule. The counting rule, that means for each the node, we just to count how many shake hand, and continually for the B, for the C, but should be careful if just to already to shake hand. For example, A to shake hand with B, so we didn't need B again for the shake hand with A again to rest of them. So it is just as just abstract the value or abstract element don't permit the repetition is just the counting rules. So maybe it is easy to understand, but sometimes if we just to for more the edge or more this node vertices, you will find for boring or for not to counting carefully. But if we just to translate this graph and using this graph the rule we have mentioned this theory as the theory, that means all the edges, some of the edges have relation with all the degrees. That means the 2 times the double edge is equal to all the degrees. And as here we can easy to counting how many, because each the person should be shake hand all the other the person. So for each the note that should have be the rest of the person, and here is all the 6 rest of the 5. So each the note have the 5 edge. 5 edge means 5 degree. So altogether is 5 times 6. 5 times 6. We have the 6 notes. So 5 times 6 equals 30. And all the degree is 2 times h. It's double h, so h is 50. So it is very easy to solve our question. But here, based on these rules.
Same thing now, if I gave you another question, instead of having to draw the graph and count things up, we can just use this relationship. How many edges are there if you have 10 vertices, each of degree 6?
So if we just based on this, maybe you are just counting or just using the counting rules. Maybe you should to count carefully. But if I just use these rules, it will make very easy.
So again, I have to think about, what do I know? I have 10 vertices, each of degree 6. So over here, I had 6 vertices, each of degree 5, and that gave me that 30. So that's all I'm going to do. 10 times 6 is 60. How many edges must I have? I must have 30 edges.
So it is just based on this equation from the rules, we can to solve out the result very quickly. But if you just use counting, you should be thinking carefully about each the node, how many the edge, how many that we should to didn't to counting each the edge, the twice should be careful. But if you just use the rule, it's very easy.
Let's talk about the terminology now related to directed graphs.
And here we just to talk about this the concept, especially for our just the degree. And degree have a relationship for our just our age. And here just have another rule, second rule, or CR2. And CR2 means that it is have the even the number of the vertices that are of the odd degree. It is just based on the first theorem, and we can to get this second the rules, just because it is just to about some the degree of the node and about the order the degree. It is also should follow about this because we know that all degrees should be double edge. That means all degrees should be even number. All the degrees should be even the integer number. So just from the theory 1 or rules 1, we know that all degrees should be the even number. So for the odd, if for the edge the odd the degree, then you should have the even number. For example, if you just have only for the odd edge, you are only for the 5 degree, and all other is even. For example, other is even. So altogether is 15. It is not even because all the degree should be even number. So the all the degree for some vertices, then you should be careful. It should have the even number. Then that means if you just have one order degree, you should have another order degree to get this sum together. Then it should be even. It's just based on from our case. So this is a proof. That means just from this, it is just because we have all the degree should have these 2 times. So you can just to derive the degrees can be seen the even degree and odd degree, and all together is just the vertices is just the V1 plus V2, and all should be these degrees should be degree V1 and degree V2, all should be together. It is a double. It's a double edge, so it is even. So the even, there's no problem, and even plus should here also should be even. So just from the number theorem, we know that all the degrees should be have a even number of the vertices. Otherwise, we cannot satisfy this double. Okay, just because here have the double. It is just because here have the double. So here is already even, and here is odd. Okay, but the V2 is odd. So here is odd number, and this odd number should be the even times. You just plus even time. You just odd time. For example, odd time, that means 5, 7, and 3. It is odd number. You add the odd times, then the final number is odd number. It is 15, so it is odd number because for all the odd number, we just add the odd times. That means you should add the even time. Even time, that's in the problem. For example, it is we just the 4 times, also the even, for example, 9 is just 24. It is the even number. So it is just based on the number theory. Okay. If just for some the digraphs, we also have this concept, but they should be careful. This concept we have the initial vertex and terminal vertex. Initial vertex, because we can say it began, it is have an arrow for each the edge they have arrow, so it is adjacent. It is just from U to V, but they should be careful for the digraph. They have a direction. So then we have begin from this arrow began from U to V, and the begin node we call initial vertex, and the end node we call it the terminal vertex. So it is just like this. And for degree, because if you have the indirect graph, they have no arrow. So their degree is just combined together. But for the digraph, they have, because we know that for the digraph, they have just the arrow. Arrow means that it is, we can say it is in, it is out. So for example, here A and B, they have edge from A to B, so we can say A is out edge, and B is in edge, because it is have direction. So from this node out, we can say it is out edge, and it come in. It is arrow come in. So for B, it is in edge. So for the degree, we also to derive in the digraph, directed graph, is just to have an in degree or out degree. Just connect with the in edge and the out edge. Because we know that the concept or the definition from the degree, it is just equal to the sum of all the edge. But now the edge have a direction. So we just for this direction have the in edge or out edge. So degree just we have in degree we counting all the number of the in edge. Out degree we counting all the number of the out edge. Okay. So it is just like this. Then we have the similar the rows 1 and we have row 3. Series 3 for the degree and edge. That means just like this. This edge is all the edge equal to all the in degree, also equal to all the out degree. Out degree. It is just for easy to understand because in the digraph for each the direction edge, we will just contribute one in degree and out degree. So they are just for this, and for the rows 1, they're also satisfied. That means all the together we can say it is 2 times edge. The double edge also equal to this. Just say this in degree and out degree. Okay, out degree. And for the diagram, we also find from this row 3 means that the in degree and out degree they are equal. Because we know that for each the edge, there are only one in degree and out degree. So they are just for have the average have the same. Okay, just also to show about more examples from the video.
So directed graph is just another kind of graph, again, where the edges are connected. So we still just have vertices as we normally would. Vertices, obviously the plural of vertex. But now we've got some additional terminology because we care about the order. So if I'm looking at this guy, obviously, whoops, I went the wrong direction. A maps to A. So A comma A would be some value.
And here we also mentioned that all the map graph, it is a description about our relation, the relation A and B from this many nodes, and then also similarly can be described or the orange definition or the set relation set. So here just you will just describe this graph or this relation graph. We can just describe about this relation set.
A does map to B, but if you'll notice, and again, that's because the arrow went from A to B, but there is no value from B back to A. So the order does make a difference. So keeping that in mind, let's talk about some of the terminology. And I'm not going to continue to list everything out, but let's talk about what the terminology is for these specific graphs. So before we just said adjacent to, meaning that they were connected with an edge. And now we're saying, yes, you can have adjacent to and adjacent from. So we're going to look at some examples specifically using this ordered pair A comma B. if we were using the term adjacent to, we would say A is adjacent to B, but B is adjacent from A.
So here, if just for undirected graph, then adjacent will have no direction. But for the directed graph or digraph, adjacent they have a direction. So how to describe this direction? We just using the different words, the to and the from, adjacent to just like this, A adjacent to, so it is out. Adjacent from can be seen as the in. B is adjacent from A, so you can say it's from, that means it's coming from A coming to B, like this.
So the initial vertex is that first vertex, but the terminal or end vertex is the second vertex. So again, it's pretty easy terminology so far. And now let's talk about in degree and out degree. So if we're talking about the in degree of a vertex, the in degree, and again, notice the notation, the in degree is essentially all of the, or adding up the sum of the degrees of vertices going into that point. So let's take a look at B, just because we're picking on B today. So if I looked at the degree of in, or the in degree of B, I'm saying how many edges go into B. So I've got 1, 2, again, because these are arrows in. So the in.
So here should be careful for the diagram. There are degree, have a direction, they have an in degree and the out degree. In degree, if we just count in degree, that means this arrow connected with the B. And for the out degree, that means arrow from out from B.
Degree of B is 2. What is the out degree of B? It's how many are coming out of B, which is just 1. So again, that is the out degree, and we're just using the plus instead of the minus. So the very last relationship is very key. It's one of those things we're going to use not only in this class, but if you continue on to Discrete Math 2 or Combinatorics, where you learn more about graphs and trees and all of those fun things, you're going to use this relationship. This relationship helps us to know, essentially, you're going to get a question like, if the number of edges is this, what's the sum of the in degree, out degree, etc. So let's talk about the relationship. This relationship says the sum of all of the in degrees is equal to the sum of all of the out degrees, which is equal to the number of edges. So of course that just means it's the cardinality of the set of all edges, which is the number of edges. So we could go through and we could count that up for A, B, C, D, and E. And we could verify that that's in fact true for this graph, but let's not do it that way. Let's think about it logically. Let's say I'm going to add this guy right here, going from B to C. So if I were to add that, then I'm going to add an edge. And that's going to add 1 to the in degree right here. And it's going to add 1 to the out degree right here. So it makes sense that every time I add an edge, I'm adding both an in degree and an out degree. And that's all that relationship is saying.
So from this session or from this view, we can easily to understand why your age, number of age equal to all their out degree and also equal to in the degree, because when more the age or this direction edge, they have just an arrow, then they contribute the 1 in degree and out degree. Just one more, it means one more edge, one more direction edge, you will get one more degree in degree and one more out degree. Similar for all the edge, you can say just simplify like this. So it is just to give out this. Then this is an example. So just to show you our about these similar things. And here just give the more about the concept. And this concept just means by the patched graph. It is can be said it is a party, but it is just only means that it is vertex and point with just the edge. It means if it just their vertex and the edge is a set, but the set should be careful. It is just can be divided into here into just the disjoint. That means the non-empty set, the two set is all the vertex set and just divide the two set, and these two sets should cannot be any the common. For example, here, for example, it is just like this. We can do this part, and here is another part. This is V1. This is the vertex set V2, and then we can say this two part is the vertex set. They have no common set. It is just means disjoint. The join non-empty set is just mean that it is say it is just like this. And similarly, if it just from this and from this, it is also the same. Okay. Okay. Now we just have the 5 minutes break.
And I want you to
Okay, we continue to talk about our graph, and in the early about this session, we just to talk about our graph, some the more the concept for the indirect graph or direct graph. We just have adjacent and we have the degree, we have these two, the basic, the concept, and adjacent means that it is just the connect the two nodes using the edge. And even for the indirect graph, it is just directly, but the direct graph, they have arrow, they have a direction. So for the adjacent, we also to separate for the different the meaning. That means we have the adjacent to or adjacent from. It is referred to just the in edge and out edge. And for the degree and in direction degree or directed degree, we also have a different concept. That means for the indirectly we have a general concept of degree. It is just to counting how many the edges connect with the node. And for the directed graph, that means for each of the node we have the in degree and out degree. It is referred to the in edge and out edge. Okay. And also we are just the last of this. We have just have this the special graph, the biparty graph. This biparty graph, that means we sometimes we want to just to divide our the graph the node with the node set the two vertex set, and these two vertex set have no common part. That means they have no the common vertex between these two vertex set. So it join. For example, this may be, and sometimes you can say you just like this. For example, this is the vertex 1 and the vertex 2. So it is no common. And similarly for this, you also can just like this. Okay, this is the vertex 1 and the vertex 2, and then they have no common vertex. So it is can be seen. It is the party the graph just depend on how to derive this, and then you can say all of them just with this. Okay. And here is just the theorem in that a simple graph, and we call what means a simple graph, and we have mentioned a simple graph. That means we don't permit the loop. We don't permit the loop. Here is a loop. Is a loop. We don't permit loop edge, and also we don't permit this the multiple edges for two nodes. We don't permit like this. So even though this no loop edge, no multiple edge, this is a simple graph. So you will find this is a simple graph. For each of the two nodes have no more edge, there's only one edge. Okay. So a simple graph is biparty if and only if it is possible to assign one of the two different color to each vertex so that no two adjacent vertex are assigned the same color. So it is mean that if just the two together, you using the color, then you can say you can to using the combined together. But for example, here, if it's just this, if it's just the vertex this, and here is another vertex set, then these have no, for each these have no just means. Then we can say you can using, if you're just using the color, then you can to combine their means. But if you just for using, sorry, for example, the edge, that means you cannot do that. So this is just just like this. If you just to combine, for example, here. That means if you just here A B, you can say here A B, and here just like this, and you can say to bind for them is different from this set V1 and here is V2, and from the edge you can just from here and here you can use the two different color for the different text. So and for each the connect, because these have no the connect, all of them is come here. But here is difficult. For example, if it's just like this, they are just the connect have the same color. So it is cannot be the biparty the graph. Okay. And here is a complete biparty graph. Complete biparty just like this. It is mean that, for example, we have already the two part is here and here. Then we can say each the edge for this node, for each the second part for this, for example, A, and here is just to say A1, here is A2, here is B1, B2, B3, and then for each of these nodes have two other parts to have an arrow or have just have this edge connect with the other part. Then we can say it is complete. And similarly here is have the 3, and also have the 3, and then for each of the node they have just to connect with the other part of each of the node. And similarly, they have the bottom. Also each of the node connect also the top part node. So we can say it is just the complete biparty graph. Okay. And for just more example from the video, maybe easy to understand about this complete graph. Okay.
Notice the notation K sub n. And essentially, it is a simple graph. So remember, a simple graph doesn't have any double edges and it doesn't have any loops. So it's a simple graph that contains exactly one edge between each pair of n distinct vertices. So I've drawn some of these out for you. I know my abilities in drawing graphs is just staggering. You're welcome. But this is K1, and K1 obviously means that there is just one vertice, which means there's not going to be any edges because we can't draw a loop or it would not be a simple graph anymore. K2 is 2 vertices connected just by one edge. K3 is 3 vertices. You get the idea? Okay, four vertices, and notice each one is connected to each other one.
So for this, we have just this complete graph. It
connected
is just
to each other one. Two other types of connected to each.
It's a complete graph that is have many concept. It is just have maybe just have a course, just the structure for the graph. Maybe you have just have a meet or base many concept. And here we just give you the general and some of the popular concepts such as a complete graph and the biparty graph, and it is just to give you the simple understand or introduction about this concept. Okay, so it is just to have give you the simple examination or simple just the introduction about this graph or the different graph or just the graph, the concept, okay, is complete graph. So complete graph just means for each the node should have be arrow or should be have this edge, this interacted graph or edge other than the rest of the node. For example, if just the 4, then we can say for each of the nodes they have the 3. So you can find the each of the nodes have the rest of the edge. So each of the nodes have the same degree. This degree is equal to this how many the nodes. For this K4 is the degree, each the node degree is 3, 4 minus 1. And the K5, that means have the 5 nodes, so each of the nodes have 4 degree, because they should have connected with the rest of the node. The rest of the node here, K5 is 4. Similarly for 6, 6, that means the rest of the node is 5. So each of the nodes should to connect the rest of the nodes. So each of the nodes have the degree 5. Okay. So it is just like this. And continuously about more the concept, maybe.
Two other types of special graphs are cycles and wheels. So a cycle can only occur when you have at least 3 vertices.
So we just to you more quickly about this concept. We maybe didn't talk more just from this concept meaning, the word meaning cycle and the wheel. Just from the picture, you will find it just the loop or circle like this, and here just the same as the have a wheel. It's the wheel. Okay.
Which of course makes sense because if I had 2 vertices, it would just be one edge connecting them. But a cycle essentially says that I'm going to continue to connect V1 to V2, V2 to V3, V3 to V4, V4 to V5. So I'm connecting them in the correct order all the way till I get to whatever my last value is. So Vn minus 1 to Vn. And then Vn, my last vertice, to my first vertice. So Vn back to V1. So again, it makes sense that this is called a cycle because it's just going to connect all of the values with none of the other extras in between. A wheel is what happens when we take a cycle and add just one additional vertex, essentially in the middle, and connect it to all of the existing vertices. So for instance, here's C3, the cycle for 3. If I take another vertex in the middle and connect it to each of the existing vertices, notice now that's W3.
So this is very interesting for this concept. Although we didn't mention in our slide, but in the video, it is very interesting to give you an introduce about this more concept, cycle and wheels. So it is very interesting for this meaning.
Wheel with 3 vertices. And then C4, again, is a cycle with 4. I put another vertex in the middle and connect it, and now all of a sudden it's W4. And so you get the idea here. An N-cube or a hypercube is another type.
So this is a cube, just like this. You will find these all the nodes and edge combined together. You will find it is very similar as the cube with the cubed picture. So we just call it, and sometimes maybe it is very interesting for in the future, maybe especially for the computer science major. That means they are read about this just the bit position, just using about all these things.
Of special graph, and we can see the notation here is QN, and that's what tells us that it is a hypercube. And essentially what happens is we have a graph with vertices representing the 2n bit strings of length n. And it's obviously multidimensional as you get larger and larger and larger. And each adjacent vertice differs by exactly 1 bit position. So if you'll notice, what happened here is I have 2 bits. I have 0 and I have 1. It's this guy and this guy. And all I did really was then double that. So I took a guy here and said, well, this is 0, 1. And I took a guy here and said, this is 0, 1. And on this one, I added a 0 in front. And in this one, I added a 1 in front. And then I connected the dots. And then I took that square, and that's my little note over here. I took that square and I doubled it. And I added a 0 in front of the bottom ones and a 1 in front of the top ones. And then I just connected. So that is how we construct a hypercube.
So just to show about this, the hypercube, it can be seen as like this, and here is the general the cube. Very just can be described on the bit strings. Okay. And here
Next,
is the
let's take a look at
graph.
bipartite graphs. Now, bipartite graphs are not quite as relatable to things like computer networking and things like that, like our last example of hypercubes were. But it is something that you'll see quite often throughout graph theory, and it does have to do with partitions. And so it's a simple graph, meaning that there's no loops and there's no multiple edges, but it's called bipartite if essentially I can partition the vertices into 2 separate sets such that all of the vertices in my first set are not connected to one another, and all of my vertices in the second set are not connected to one another, and the only edges that exist go from one subset to the other, which is exactly what I have here. So notice here, A is not connected to B or C or D, and 1 is not connected to 2 or 3, but I can have an edge that goes from set 1 to set 2, and from set 1 to set 2, and set 1 to set 2.
So that is why we just have this bipartite graph, because we know that our graph just want to describe how the relation set or relation just the table, or we have the relation the matrix. But if we just use the map, then we can say this is just the input and here is output. So we just divide the two disjoint the taxi set. That is why this is the 2 different domains. And here is the input, and here is output. So for the general graph theory, we sometimes want to use this special graph. We call it just the bipartite graph. That means we have just to divide the 2 parts for a graph, and some part can be seen as the input domain, and out part can be seen as out domain. So from this, we can just as a map graph. Map graph, you can say is similar as the just the map from S1 to S2. Also here S1 is a subset, and S2 also is a subset of the graph vertex is set.
Now that we know what a bipartite graph is, we want to take a look at how to determine if a graph is in fact bipartite. So as you can see, I have two graphs here, and neither are written in the normal bipartite graph form, where I have two subsets that are distinct. So the question is, can I essentially redraw this graph so that I have two distinct subsets? So let's start by using a graph coloring technique. What I'm going to do is I'm going to choose a random vertex. In this case, I'm going to choose A. And again, the normal bipartite graph form is that I'm going to have two subsets. So essentially what I'm saying is I'm putting A over here. And I'm saying, what can I put in the other subset? So I'm going to put things in the other subset that are connected to A, like G and F and E and C. So G and F and E and C. So by redrawing it, I would now have an edge connecting AG, AF, AE, and AC.
So here you will find it similar. We just want to connect or just to construct the relation map. But for the graph world, they didn't care about whether or not their map just have the graph for example, the loop or the multiple, and maybe they have many things. But we only to care about our map, our relation map or relation set. So here we just using the one to the bipartite graph, and then to connect or to separate out the two disjoint the vertex and to same as our the maps to different domain, input domain and output domain. So we are just using this color. That means we are first select them just as a map. So the other side, it is the other side part.
Now, before I continue, because obviously I still have B and D, I need to determine, would there be any lines connecting G to F, G to E, G to C? And the answer there is no, just by visually inspecting the graph. F to G, F to E, F to C, no. E to G, E to F, E to C, no. And of course, I don't even have to check C because I've checked it with all of the other vertices. So far, this side is okay because none of these vertices are directly connected to one another. So now what I do is I say, if I have a vertex connected to a blue vertex, then that must be green. So looking at, for instance, G is connected to D. So I'm going to color that green. And then I have to look at D and say, okay, is D, that is green, only connected to blue vertices? So I've got a blue vertex there, a blue vertex there, a blue vertex there. So yes, so now I'm going to add D over here, and I'm going to connect it to G and to F and to E and to C. So D is connected to all four of those blue vertices. And then I'm going to look at B. B is connected here to a blue, so we have to color it green. Remember, we can't have two of the same color connected to one another. So green to blue, so B to F and B to E and B to C. So yes, this is in fact a bipartite graph because I use the graph coloring technique to determine it. Now,
So if you just to determine whether or not your graph is just have the bipartite graph, that means we can easily to give the set. For example, we have mentioned just with the top, the G, A, B, C, and the bottom, F, E, D. This is no problem. But if we just to check whether or not can be seen as a bipartite graph, that means you are just to separate about the map into two different domain, and each the domain should be careful. They have no just the intra edge, or we just the map only have the inter edge. It means it is just have the map only from the input to output. So here just give you to select how to select about, and finally you will find APD should come together. So if you just to for simply to circle the top and bottom, maybe it is no problem for just the node itself, but you should be careful. It is the edge. This edge is different. That means it should be satisfied about this separate, or it is the input and output of the domain. So using the color maybe is very easy, or just to check. That means you can just using the color, you just connect, then you should another color. For example, you just to make the A node color green. So for all the just the connect should have the different color. Here is a green or blue color, okay? And but if you just to for other, here the D, because the D is connect with the E, so D should be a different color, and the different color is here just using the green, and E is the green, so here is the C, so no problem, okay? And here is the, and last is the B. And B, because connect with the C, and C are already the blue, so your just the B is a green. So it is no problem. But for F, for H, it's difficult to give the party.
I want to point out to you that this is the same graph. They're actually called isomorphic. This is the same graph, just written in another way. So it's got the same vertices and the same edges.
So you will find just just the relation map, or here is the relation map, and here is the general graph. So we are just to say that all the relation map can be referred to biparty graph. So that is why we introduce biparty.
Da, Surinti daw. Neso, চামচ রই আমার। ও বাম্মা দা হ্যাঁ দাও।
না জানা তো এমনি এমনি দেখ কেউ সাথে
রই